Let's now look at an example where we will need to use what we learned about linear differential equations and how to solve them to figure out the application. Consider a clean pond that holds 10,000 cubic meters of water and has two streams running into it. Water from stream A flows in at 500 cubic meters per day, while stream B flows in at 750 cubic meters per day. Water flows out of stream C at a rate of 1,250 cubic meters per day. So in total, the amount of water coming in is equal to the amount of water going out at the beginning. And then, at time t equals 0, stream A becomes contaminated with road salt at a concentration of 5 kilograms per 1,000 cubic meters. And also at time 0, someone begins dumping trash into the pond at a rate of 50 cubic meters per day, causing the rate of water flowing out of stream C to increase to 1,300 cubic meters per day. The idea here is that the total volume going in is 1,300 cubic meters, 1,250 cubic meters of water, and 50 cubic meters of trash, so the rate out must also be 1,300 cubic meters per day. But all that's coming out is the water. In this situation, let's let S of t be the amount of salt in the pond after t days of pollution, and we want to find this function S of t. To find S of t, we will need to model S of t using a differential equation. To do this, we will want to look at how S of t changes, distinguishing between the rate at which salt is coming in and going out of the pond. For the rate in, we know that the salt is coming in from stream A. It's coming in at a concentration of 5 kilograms per 1,000 cubic meters, and each day 500 cubic meters of water is coming in from stream A. Taking the product of the concentration of salt in the water with the rate at which the water is coming in each day gives us the rate at which the salt is coming in. And similarly, in our calculation of the rate out, we will want to take the concentration of salt in the water times the rate at which the water is leaving the pond, though we'll have to work a little harder to find that concentration. Before we do that, let's simplify the rate in. 5 kilograms per 1,000 cubic meters times 500 cubic meters per day will have the units meters cubed cancel, and we'll be left with 2,500 kilograms per 1,000 days, which simplifies to 2.5 kilograms per day. So each day, 2.5 kilograms of road salt is coming in from stream A. To do the same thing for the rate out, we'll need to know that concentration. The concentration of salt in the pond is going to be the total amount of salt divided by the total volume of water in the pond. The total amount of salt is given by S of t. So the concentration will be S kilograms of salt per total amount of water in the pond. Now, at the start of this process, there was 10,000 cubic meters of water. But remember, each day 50 cubic meters was replaced with trash. So on any given day, there will be 10,000 minus 50 times t, where t is the number of days that it's been polluted in, cubic meters of water. So here our concentration is S kilograms of salt per 10,000 minus 50t cubic meters of water. And that concentration we'll need to multiply by the rate at which the water is going out of the pond, 1,300 cubic meters per day. Multiplying these and canceling units, we'll have 1,300 S over 10,000 minus 50t kilograms per day. And combining these, we get the differential equation ds dt is equal to the rate of salt coming in minus the rate of salt going out, which is 2.5 minus 1,300 S over 10,000 minus 50t. So we've now modeled S of t with this linear differential equation, which we can write in standard form as ds dt plus 1,300 over 10,000 minus 50t times S is equal to 2.5. And now that we have it in standard form, the next thing we'll need to do is solve it using an integrating factor. We can find this integrating factor as mu equals e to the integral of 1,300 over 10,000 minus 50t dt, our coefficient of s. Computing this integral, we get that the integral of 1300 over 10,000 minus 50t dt is negative 1300 over 50 times the integral of 1 over t minus 200 dt by factoring out the constant 1300 from the top and negative 50 from the bottom, which is equal to negative 26 1300 over 50 times the natural log of t minus 200 by making a simple substitution, u equals t minus 200. And then of course at the end we'll have plus some constant of integration, c. So we can choose the integrating factor to be mu equals e to the integral of 1300 over 10,000 minus 50t dt, which is e to the negative 26 times the natural log of t minus 200, choosing c to be 0, which can be split up as e to the natural log of t minus 200, all raised to the negative 26 power. And we make this change because e to the natural log of t minus 200 is simply t minus 200. So we can rewrite this again as t minus 200 to the negative 26th power. Using this integrating factor, we get that s equals 1 over mu, which is t minus 200 to the negative 26th, times the integral of 2.5 t minus 200 to the negative 26th. We can pull the constant 2.5 out of the integral and simplify 1 over t minus 200 to the negative 26th to get 2.5 times t minus 200 to the 26th times the integral of t minus 200 to the negative 26th dt. In computing this integral, we'll have 2.5 times t to the negative 200 to the 26th times negative 1 over 25 times t minus 200 to the negative 25th plus some constant of integration c. And distributing 2.5 times t minus 200 to the 26th in, we'll get negative 2.5 over 25 times t minus 200 to the 26th times t minus 200 to the negative 25th, which simplifies just to t minus 200, plus a constant c times t minus 200 to the 26th. Please note here that I abused our constant a little bit. I replaced 2.5c with c again, but it's still just some constant. So this gives a family of solutions to the differential equation. But what value of c should we choose for this particular application so that we just have one function modeling the amount of salt in the pond? We know that S of t is the amount of salt in the pond after t days of pollution, and S of t we found to be negative 2.5 over 25 times t minus 200 plus a constant times t minus 200 to the 26th, where the first coefficient can be simplified as negative 1 over 10, but we still need to find what c is. To do this, let's note that we started with a clean pond, meaning that at time t equals 0, the amount of salt in the pond was 0 as well. So we have what we call an initial condition that S of 0 is 0. Using this in our formula for S of t, we get that 0 equals S of 0, which is negative 1 over 10 times 0 minus 200 plus c times 0 minus 200 to the 26th. And simplifying this, we'll have negative 1 over 10 times negative 200 is 20, and negative 200 to the 26th is simply 200 to the 26th, since we are raising a negative number to an even power. So we have 0 equals 20 plus c times 200 to the 26th. Subtracting 20 and multiplying by 200 to the negative 26th on both sides, we can solve for c as negative 20 over 200 to the 26th. And using this particular value of c back in our equation for S of t, we can conclude that S of t is negative 1 over 10 times t minus 200 minus 20 times t minus 200 over 200 to the 26th power. Simplifying that 1 over 200 to the 26th times t minus 200 to the 26th can be written as t minus 200 over 200 to the 26th power. So having an initial condition, knowing the value of s at a particular value, we were able to find one solution that satisfied our differential equation and that initial condition. In general, we will need an initial piece of data in order to narrow down our family of solutions that we have been finding for our differential equations to one solution that satisfies the initial condition and the differential equation. We'll see this more throughout the course.